Linear programming addresses a strictly defined mathematical challenge, determining the absolute best way to allocate scarce resources among competing activities. We can model this by looking at a manufacturing firm that produces two distinct items. We have sleeping bags, designated as variable x1, and tents, designated as variable x2. The firm's single objective is to maximize total profit. Based on their margins, every sleeping bag yields $50, and every tent yields $30. If resources were infinite, production would be infinite, but physical constraints cap daily output. The factory is limited to 14 hours for cutting, 40 hours for sewing, and 18 hours for waterproofing. Because we are only tracking two products, every conceivable daily production schedule, no matter how impractical, can be plotted as a single coordinate point on a two-dimensional plane. A resource limit acts as a mathematical wall, separating possible schedules from impossible ones. When we plot the 14-hour cutting limit, the line slices the coordinate plane. Applying the sewing and waterproofing constraints restricts the space further. We are left with a closed polygon at the origin, the feasible region, representing the finite boundaries of reality. Even within this restricted polygon, there are theoretically infinite fractional coordinate points, representing different production mixes. The challenge is proving which single point yields maximum profit, without having to calculate every single possibility. The geometric solution to testing infinite points is a tool called the iso-profit line. An iso-profit line represents all the different combinations of tents and sleeping bags that result in the exact same total profit. To find the highest profit without changing the slope, the iso-profit line shifts outward, perfectly parallel. Moving through the feasible region maps higher yields. To maximize profit, it slides out until it catches on the outermost vertex, point D, producing 6 sleeping bags and 2 tents. This visual behavior is formalized as the extreme point theorem. The theorem states an absolute guarantee. If an optimal solution exists in linear programming, it will always occur at one of the extreme boundary points, or corners. Re-examining the bounding lines, if we extend the constraint equations infinitely, we find exactly 10 distinct intersection points. Half of these theoretical intersections violate our physical resource limits. Filtering out non-feasible points leaves only the specific few lying on our actual boundary. The geometry of linear programming radically downgrades an infinite search space into a simple, finite checklist of just 5 distinct corners. Graphing provides a clear visual proof, but it has a fatal flaw. We can only graph 2 variables at a time. Real-world optimization involves dozens of variables and hundreds of constraints. To scale this concept beyond a two-dimensional plane, we have to translate these geometric truths into high-dimensional matrix algebra. The first step is to convert our original less than or equal to inequalities into strict equations. We do this using what are known as slack variables. Looking at this text block, we convert the inequalities by adding separate slack variables, S1, S2, and S3, to each constraint. These represent unused resource time, balancing equations perfectly. We've now structured our word problem into a clean algebraic system with 3 equations and 5 variables. The pure mathematical equivalent of visually locating corners on a graph is called the basis theorem. The theorem dictates a strict algebraic rule. In any system with n equations and v variables, setting exactly v minus n variables to 0 forces the math to land precisely on an extreme point. This combinatorial formula calculates exactly how many of these mathematical extreme points exist in our matrix. By plugging our 5 variables and 3 equations into the formula, the math resolves to exactly 10 basic solutions. Those 10 mathematical permutations calculated by the abstract basis theorem perfectly mirror the 10 geometric intersections we graphed earlier. Whether you are plotting 2 variables on a piece of paper or optimizing 50 variables in a supercomputer matrix, the rule of optimization holds true. The answer is always waiting in the corners.